This question is very much like question 5. We have a light source that emits two wavelengths. We are given the separation of the slits by being told how many slits we have per millimeters for this grating, and we are given the distance between slits and the screen. Again, it's very much like this question here. The difference is we have a grating instead of a double slit. Because of the grating, we have to calculate what D is instead of it being given. Calculating it is easy. If we have 250 slits per millimeters, to find how many slits, what is the separation of the slits, we just take the inverse of that number. D is 1 over n. So 1 over 250 slits per millimeters would give us D in millimeters. In this case is 0.0040 millimeters, which is about the 10th of the distance that we were given here, separation of the slits. Since we are fitting many more slits in a smaller space, the slit separation is small. Now the question though is asking for the angular position of the third order principal maximum. It's not asking for the position on the screen, it is asking for the angular position. So we use the expression for the angular position, which is d sine of theta sub 3 is equal to 3 lambda. That's for the third order maximum, and we solve for theta sub 3. That's easy. D being 1 over n, just work it out. Notice the angle we find here, 21.1 degrees. That's quite a large angle. We cannot assume that to be a small angle. Now, question B asks what's the position on the screen of the third order principal maximum. So they are asking us here for y sub 3. Except we cannot use this expression anymore to find y sub 3. We know what theta sub 3 is. The thing is, this expression of y sub n was developed assuming a small angle approximation. Okay, for example, here, this is where my double slit is, and this is where my screen is. So the central maximum is going to be if I go in the middle of my slits and go all the way to the screen. This is where my central maximum is going to be. Now for any other maximum, it's going to be off of that central maximum. So for example, I can have one maximum here. If my third order maximum is here, that would be y sub 3 from here to here. This is theta sub 3. In the small angle approximation, this distance, which is this side of the right angle triangle, is about equal to the hypotenuse. They are not much different. But when we have large angles like 21 degrees, they are not equal. So we have to use this more accurately, represented more what the sides are. We know the angle here is 21.1 degrees. We know the angle. We know the distance separating the slits from the screen. That's L, the 1.2 meters. So to find y, we remember that the opposite over the adjacent is the tangent. So y1 sub 3 over L is the tangent of theta sub 3. And we solve for y1 sub 3 that way, using the tangent expression. So it is L tangent theta sub 3. That's the position. Now question C, it tells us what is the angular position of the third order principal maximum for the second wavelength. And then what's the position on the screen of the third order principal maximum for that line. So we use the same process. Oh, sorry, here I still get that tool. Okay, so let's so we don't have that tool now highlighted anymore. So we solve for theta sub 3 for that second wavelength. So it's 24.8 degrees instead of 21.1 degrees. And y2 sub 3 is L tangent of theta sub 3, which comes out to be 0.555 meters instead of here where we found 0.0463 meters. The separation of the fringes then is the separation of these two. 0.055 meters minus 0.0463. Then the next question is how would the central maximum look? And the central maximum should look very much like the central maximum looked for question 5, except now our central maximum is going to be much narrower and brighter. Now, question G, focusing on other fringes, would the light colors also combine for these fringes? For question 5, we said they might combine for some, they might not combine for others. Where they combine is going to differ relative to what bright fringe is. Now in this case, because the fringes are going to be narrow, in most cases the bright fringes are not going to meet at the same location, thus they are not going to combine. And that's why actually we use gratings for spectroscopy. They allow us to separate different light wavelengths by comparing, most of the time, just the first order maximum.